Now we are talking about the chicken and the egg. Who comes first? Causality. In Norwegian, kausalitet. It's not a word that we use much in general life, but we use this to find the state equations and to find them easy. So the problem at hand, you have a bond graph, and whenever you have an resistance, compliance, inertance, you will have one equation. If you have transformers, gyrators, T and G, they will be two equations. And you have junctions, zeros and 1, like that. They will give one equation each. So yes, you can set up a bond graph. Yes, you can find all the equations involved. So yes, it is possible to say find the state equations. But boring and can be a very big job. So no, we don't like this. We don't want to do it. The causality, that is something now that's going to help us finding just the equations we are interested in and nothing else, without having to go through all these messy algebraic problems. We will now start with sources. Sources are sort of the easiest one. So you can think as follows. Start with, say, an effort source here. And this effort source, he sort of gives an effort, and this effort is now attacking an entire system, whatever that is. System can be a big, complex problem. And this problem, now we're going to respond with, okay, if you are pushing this effort into the system, then the system can respond with this flow, Q dot. So here, effort causes a flow. And if you look at a flow source, it's just the opposite. Then you let the flow attack the system. Here, big system. And then the system will respond with, okay, if you really want this velocity, this flow, this speed, then you're going to have to use so big an effort to do that. Last lecture I said, for an effort source, we are normally not interested in the flow, or vice versa. The flow source, we are not interested in the effort. It's something that the system will have built in anyway. So normally we'll just put a cross over these. But this is actually what's happening here. So for an effort, yes, an effort source is the effort hitting into the system. So the notation, some books will actually use these small arrows back and forth for the flow and the effort, describing which goes where. But for us, we will use these the bond, and then just a casual stroke. So here I will always do it like that. Casual stroke, think of it like this, the effort always towards the casual stroke. So when I set a stroke here, what I actually mean is I have an effort that goes into the stroke, goes into the system, whatever it is that's coming to the right here. And then the system will respond to with a flow. So, but I don't draw these half arrows, these arrows, I just draw the stroke. For the flow source, it will just be a stroke here. Important, this has nothing to do with the positive direction. Here the direction is this half arrow saying positive direction. So when we are talking about a source, we will always say sort of the power is flowing into the system in both cases. The source is flowing into the system. For a sink, it will just actually be the other way around for these arrows. Then we have been taught already we don't use sinks, so just forget about it. My point here is these causality strokes, causal strokes, nothing to do with the direction positive and negative. An effort source will have the causal stroke here. It's the effort that goes to the right, regardless of your point of positive direction, whether it's a source or a sink. And same goes with the flow, like that. But we don't use these two, so actually just forget about them. That was sources. Effort source, flow source. What about this one? Source real. What should he have? Well, a real source, that's a real pain. Like we have in exercise 2 now, you have the motor given the characteristic curve, torque versus rotational speed. So it's neither an effort source nor a flow source. So for a real source, we can't use causal strokes, causality. And that is sad. Then we are back here. Okay, we can find the equations. Then we have to do it the long way. Yes, it's possible. With a real source, that's actually what we have to do. Sometimes we can cheat. We know the source is real, but let's treat him as an effort source, although he's not an effort source. He's actually a real source. So sometimes we can get away, but in general, can't use causality. Must use the pure algebra. That was sources, effort source, the causal stroke away from the source, flow source, causal stroke towards the source. Next is the junctions. What about the junctions? Well, that's also a question with the chicken and the egg junctions. A zero junction, that was common effort. So here I have a zero junction, and then say a couple of arrows going in and then a couple of arrows going out, for instance. Something like that. Now, it's a common effort. That means the effort on all these bonds must be the same. So effort, 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 effort. It's the same effort everywhere. But only one will be allowed to decide what should this effort be. Only one. What does that mean with the strokes? Only one bond. One bond decides what the common effort should be. Only one is allowed to do that. Only one is in charge. Which means, say now it's this guy, he decides. Then I put a cancel stroke here. This effort goes like this into this one junction. Now this bond, he dictates what the common effort should be. Meaning the rest of the strokes has to be away from this zero junction. No question. That's the way it has to be. Only one bond is allowed to decide what this effort should be. So for a zero junction, only one stroke towards the zero. Everybody agrees with that one? Common effort junction. Okay. Then for the one junction, common flow. Same things here. Only one bond. That should decide what this common flow should be. So we have a one junction here. Some bonds entering, some bonds exiting, and okay, this Q dot to the left there, he should decide. Where should now the causal stroke be? Well, it has to be opposite from this effort thing, so it has to be here. Now I know the effort goes to the left, always towards the stroke. The flow goes away from it. So now it's this flow entering the one junction and thereby deciding what the common flow should be. Meaning all the other strokes has to be towards the one junction. Like that. So for a one junction, all but one stroke towards him. You find some examples there in the text. It's actually quite boring, but you can have a look at it if you like. They call it coupled and uncoupled behavior. I can give you an example. You don't have to write this down. Say you have a flow source like this hitting a one junction, and this one junction here has a mass and a spring and a resistance, something like that. Check the causality here. Well, from the source, that is the flow source, then the stroke has to be here. It's this flow from the source that's attacking this one junction. But now I know the flow, the Q dot is given on all these bonds. So the flow is given. Then these elements, they don't talk to each other. So they sort of have three separate problems here. They are not coupled at all. So the flow for this mass is given. Okay, then regardless of the force here, the motion is given for all three elements. Uncoupled problem, it's not actually a problem, and I would say it's a waste of time. Why bother? But all you have to do is this. You use an effort source, and that's a different problem. Now you are attacking something with a force. The stroke goes here. That's something else. That's something else. Now what? For a one junction, all but one should be towards him. Now I have one towards him, but only one should be away. And I don't know which one. So now they talk to each other. Now they are coupled. Here I will have a real problem. That's something else. You'll see later on. For the ideal machines, the transformer he doesn't change anything. So if you have a transformer, then say you have found out that you have a causal stroke on the left bond, like that. That means it's the effort that is attacking. Then we know from a transformer we have a coupling effort to effort. Then if you know this effort, you can find the other one on the other side, something else. Effort 2 equals T times effort 1 or something. But the causal stroke will still be to the right. So this effort 2 will now still continue to the right. And the flow then goes the other way around. Or if you had it differently, initially you have a stroke here. Okay, then it is the flow that is hitting the transformer. The Q dot here is hitting. And then from him we will find the flow on the other side. Hence the stroke also has to be like it was on the left side. So Q dot 2 is now moving further away. So the transformer, he doesn't change anything. The strokes will be either to the left or to the right around the transformer. Gyrator, that's something else. He will change it. He will change it. G. So again, let us start with a causal stroke to the right. There on the left bond. What's happening? Well, the effort hits the gyrator. And from a gyrator, we know we have a cross coupling. The effort goes to flow on the other side. So here now you will have a Q dot that is continuing. Hence the stroke now has to be like this. So a gyrator mixes it up. He switches from effort to flow. And then also he switches these causal strokes. If you look at it on the other way, start with the stroke to the left, then what? Okay, then it is the flow down here that's hitting the gyrator. He will then produce an effort on the other side, an effort here, going further to the right. Hence the stroke has to be like that. So gyrator, he mixes up everything. Transformer doesn't change anything. Then finally, the elements, one-port elements, the resistance, the inertance, and the compliance. One-port elements. Let's start with the resistance element. Both will be quite okay. He doesn't care whether the stroke is to the left or to the right. So what should we say? Both versions is okay. So here you have a bond and you have a resistance. What's the normal connection with a linear resistance that we have with flow and effort? Well, if you know the flow, then the effort equals resistance multiplied with Q dot. Where should the stroke be when I do it like this? Well, here it is the flow that's actually hitting this R, and he goes back, and then we can calculate the efforts afterwards. Where should the stroke be? Then the stroke is to the left. If you want it the other way, resistance, and then I set the stroke here. Yeah, you use of course the same equation, you just have to sort of flip it a little bit. Now we know the effort. It's the effort that is hitting this resistance through this causal stroke, and he responds now with the flow. Q dot equals, well, fairly easy to change this equation. It's 1 over R. That's the only thing. So for a resistance, we don't mind either way. No problem there. Then we have inertance. And it's here we find our differential equations for the inertance and the compliance. The inertance. We have one that we prefer and one we don't like. So let's take the one that we like first. So here we have now the effort, also called the P dot. That is the one that should hit the element. So I would actually prefer to have it like that, because if this effort now hits this one, goes around, respond with a flow. What is this flow? A Q dot equals, and now we'll actually have the time integral of this effort. So you just remove the dot here on this P. It will be P divided by I. This is what we will prefer. What should we say here? It's an integral causality is preferred. Integral causality. Causality is okay. We like it. The differential causality we don't like. We can do it, but we don't like it. Then we have it the other way around. Then we have the I element here. So now we know the flow. The Q dot is entering. That means the causal stroke is here. We really don't like that. Sometimes it happens, but okay. So now this flow hits the element, and we can calculate what's on the other side. What is on the other side? Well, we calculate it from sort of this definition here. I want, on top, I want a P dot. From this equation, I can calculate a P alone. P is just the flow multiplied with the inertance. But then I have to take the time derivative. So here, the differential form, ddt of, and then here I will have the flow, Q dot, and the inertance. So this is the way to do it if you have to. One might think that this differential form should be the preferred. I mean, we are seeking first order differential equations, aren't we? Then we have a derivative here. But no, that is not the derivative we actually want. We have the derivative here. This is what we want. The Q alone, that's what we are seeking. Q as a function of time. So this will be one first order ordinary differential equation. If you do the derivative here, you will have a double derivative. That's a second order equation. We don't like it. We can handle it, but that was the inertance. Then finally the compliance. And the compliance will be just the opposite of the inertance. The C is also like the integral causality is okay. But here the integral causality actually looks like this. So it's the opposite from the inertance. So this means we have the flow entering our element. The flow is entering the spring, the C element, and he responds with the effort. What is the effort? Well, the effort, that will now be this compliance divided by, and then just the Q without the dot. So that is what we would like. Differential, yes, we can do it, but we don't like it. Differential causality will be little work. So it will then look something like this. So how will he look? Now it is the effort, the P dot, that is attacking. How can I find the flow? Well, again, use this one as the definition. You have to find the flow. You have to find a Q dot down here. Q dot equals, well, from the definition you can find a Q. So, no, that's not correct. Yeah, that's not correct. It's Q over C. Thank you very much. Q over C. So here you find the Q by multiplying effort and the C, and find the dot by taking the derivative. So d to t of q multiplied with the c. And again, yes, you can do it, but we don't like it. We don't like it. Yep.
Is it? Do you have to correct the rest of it? Is this supposed to be a Q?
This one?
Yeah.
No, it shouldn't be. Thank you. Effort. It's getting late. Other questions? Okay, let's see now how this finally can help us obtaining the equations that we are seeking. Let's go back to this problem that we had. Actuator. We had gotten as far as the following: an effort source hitting one junction with this laminar friction in the pipe, continuing here to a transformer, continuing to a one junction where we had mass, we had a spring, and we had an RB. There we are. Now find the state equation. That is the job. Find the state equation. We start with the causal strokes. You always start with the sources. Always with the sources. Here we had an effort source. Where should the stroke be? Well, it should be like that, away from the source. It's the effort now that is hitting the system. And the effort in this problem was actually this P source as a function of time. So there we had a causal stroke around a one junction. What was the rule about the one junction? Well, he should have all but one towards him. So he doesn't dictate anything. A resistance, he doesn't dictate anything. He could be either way. So we still don't know where the stroke should be. Then we continue further. Here again a resistance. Nothing is decided. But here we have an I and a C element. When nothing is decided and you have one of these energy storage elements left, then you can choose, always choose the desired integral causality. So let's now start with this C element. I choose this one. I choose a stroke here. Yeah. Then the C element has gotten the correct causal form. It's the integral form. Yes, I like it. This is good. Does it help me now with the rest of the strokes? Well, actually, no. I have a one junction here. He should have all but one strokes towards him. So this doesn't dictate anything. Okay, but I still have one element left. And again, here I choose the integral form. I choose the stroke here towards the I element. That was the preferred causal stroke for him. And now you see something happens. That one dictates everything for this one junction. Now we have gotten the one bond away from the junction. Then all the other bonds has to be towards him. That was the rule for a one junction. All but one towards him. Also now, since I have a stroke here, this transformer, he doesn't change anything. Then I have a stroke and a stroke. And the first one junction, he has now gotten the one bond away from him. Hence, the last bond has to be like that. So yes, we have a causal bond graph. Causal bond graph. That means all I's and C's are with integral causal strokes. Okay. I still don't see any equations, but they have to be here somewhere. So far, with annotating this bond graph, I only have the pressure. When I have these energy storage elements on the correct integral form, then immediately you can use sort of the definition. So here you will have a q dot for this C element, a q dot here, and on top the effort will be Q divided by C. Here you will write, or you should write, a circle around this Q dot, just to inform you that this is on integral form. This is going to result in one differential equation. Same goes with the I element. There we had the other way around. Here you had an effort, it was called a P dot. On the other side, you have P divided by the inertance I. And also around this P dot, you will draw a circle. This you can do immediately, as soon as you have the causal strokes, and if they are on the integral form, you can write it like this instantly. If they are on the differential form, that's a different story. We'll come back to that later. But for now, we can draw this up. To annotate the rest, we now have to follow sort of the logic here. So this is a one junction with a common flow. Who decides the flow? Well, that's where you are missing a stroke. So whatever the flow is here will dictate the flow around this one junction. Well, I don't have anything here, so I'll wait with him. What about this guy, the one junction here? Who dictates the flow? That's where you are missing a stroke. That's here. I don't have a stroke here. So the flow will be P over I. Okay, then I can write here P over I, and the flow here also P over I. Also here, but here this place is occupied already, it says Q dot. Aha, here I find my first equation. Q dot equals P divided by I. That's a first order ordinary differential equation. That was nice. Here I have P over I. Then this flow, he will enter into the transformer and give me a flow over here. What will he be? Well, here I will have to write something like this. P divided by I multiplied with T. It will be 1 over in the transformer when you go in that direction. Then you know the flow around this one junction. Then you know the flow here as well. P divided by IT. When you know the flow here, then you can find the effort on the other side. Just multiply with RF multiplied with P divided by IT. Like that. Okay, now we have all the flows. Here I have a flow hitting a resistance, then the effort on the other side, RB multiplied with P divided by I. I'm still missing something. I'm missing one equation. Where can I find it? Well, I'm missing some efforts here. Let's try. The effort here, well, he will come out of the transformer. So I have to find this effort here first. How can I find the effort here? Well, I can use the summation rule around one junction. I know the flow. And the flow here, I know it, but I'm not interested in it, so I just put a cross. But I can find this effort. I know the effort here in. I know the effort here out. Then I can find this one. Now it's going to be narrow here, so I will put a coefficient A, and then down here I write A equals, what will A be? A, well, the effort in equals effort out, so PS equals A plus this one. Hence A has to be PS of T minus this effort we have here, RF multiplied with P over IT. That's my A. Everybody with me so far? Almost there. When I know the effort here, I go through a transformer, I find the effort on the other side. Well, that will be this same A multiplied with 1 over T. And then we have the last equation. Take the summation rule around this one junction. The sum of all efforts has to be 0. And of course, what then I am seeking is an equation for the P dot. What will it be? P dot, he goes out. So then P dot has to equal what comes in here. That is A multiplied with 1 over T. Then I have something else going out as well. So that must be minus Q over C minus, and then the last one here, RB multiplied with P over I. And then we're done. There you have two first order differential equations. And you solve them. Just program and simulate. You'll find the solution. It will now be a Q as a function of T and P as a function of T. And then finally you ask yourself, what have I found? I found a generic variable Q and a generic variable P. What are they? Back to the problem. What we actually have found is Q dot, velocity for the mass, the Q, that will then be the position x. So here we are talking about table 2.1 to translate these generic quantities to the real life. What is this P? P, that is the momentum in a mechanical world. That's mass times velocity. So this P, that is m times velocity. So typically here you will divide by m just to get the velocity as a function of time. So that will be the solution to this, this problem. So this is how we are going to work with bond graphs. From the problem, you draw the graphical representation of it, use causal strokes, annotate it to find the state equation. That's sort of what we are going to do with bond graphs. Any questions? Then we continue with this tomorrow. We stop here.